Imagine a very small circuit board that contains the same chips as in today's best cell phones, GPS, 3-axis accelerometer, and a 3-axis compass. Add a microcontroller with some flash memory and a few small solid-state relays. Then for cost effectiveness, make sure this board can be mounted inside a standard junction box on the back side of a photovoltaic panel. The board is powered by the module and uses GPS data such as latitude, longitude, date, time, and declination, the angle between the true north and magnetic north, to calculate the sun's current position in the sky at the panel's location on the Earth. It also calculates the normal vector to the face of the panel using the 3-axis accelerometer and 3-axis compass readings, correcting for true north. When first installed, the operator doesn't need to enter any data or set any switch or jumper settings. The board is intelligent. By that I mean, it calculates the angle between the panel's normal vector and the sun direction vector, and then experimentally closes the solid-state relays, literally guessing at first as to how to move the panel towards the sun. The microcontroller continuously learns as it goes, storing data in its flash memory to make better and better decisions as to which relays cause what motion and in what direction. Its goal is to minimize the sun tracking error with minimal motor activations. With 2-axis trackers, this error can go nearly to zero. And with any 1-axis tracker, it will learn to do the best that it can, all 100% automatically. This means the board can work well for full 2-axis sun tracking, and with 0 changes, it works well for any type of 1-axis tracker as well, where the axis of rotation can be oriented north-south, east-west, polar, or even at some skewed angle, such as when the tracker is mounted along the slope of a hill or on a roof. This also means the tracker can be used in a completely automatic way in places not considered before. One idea is on the top deck of a moving ship. As the ship's heading changes, the trackers quickly learn to adjust, again, completely automatically. With minor modifications, this invention could also be used to automatically track satellites, whether geosynchronous or in low Earth orbit. A soldier could, for example, plop a tripod-mounted, highly directional antenna on the ground to track a communication satellite as it traverses the sky. Or amateur astronomer telescopes could automatically find astronomical objects in the night sky with no intervention at all required by the user. There are other cost-saving benefits. Photovoltaic tracker installation and maintenance is simplified. The cost of a central control computer with trenching and wiring of control cables is eliminated. Each tracker is autonomous. If one tracker fails, the rest don't. The tracking works in cloudy weather with no optics or sensors exposed to the weather, and no instrumentation is required on the face or along the edges of the panels. This invention leverages the great advances chip manufacturers have made for the tiny GPS accelerometer and compass chips, and the plummeting cost of these chips, allowing for a very cost-effective, completely new, and completely automatic way to track the sun and increase the power production of photovoltaic modules in ways that wouldn't otherwise be considered practical or cost-effective. I've built a crude but working prototype of this board, as shown here, and a provisional patent application was submitted. Thank you for considering the merits and marketability of my invention. I'm passionate about alternate energy solutions, and I'd love to work with GE engineers to fully develop this concept if funding were to become available. Thank you.